Welcome! Today we're going to be reviewing systems of equations on our Unit 8 study guide in preparation for the summative. The first section on this wants us to determine if the ordered pair that is provided is a solution to the system. So please remember that in order to be a solution, we have to be able to take the ordered pair and plug it into both of the equations to come out with a true response. So my ordered pair always has x comma y. Using that, I'm going to work with my first equation where it's 2x plus 2y. I'm trying to find out if that would be equal to 4. So fill my x value of 3 in, fill my y value of -1 in. We'll do that arithmetic on the left. 2 times 3 is 6, and 2 times -1 is -2. Trying to determine if this would equal 4. So 6 plus -2 equals 4. And so yes, that does equal 4. Check there. The second equation then wants 5 times my x value and then minus my y value to determine does this equal 16. So using my x value of 3 and then filling in that y value of -1, 5 times 3 is a 15. And when I'm thinking about subtracting that -1, I can actually think about adding 1. Does this equal 16? Well, yes, let's see, 16 does equal 16. So because we got the check for both of those, then yes, indeed, that ordered pair is a solution for us. Going over to the number 2, again, 2 new equations and a new ordered pair to deal with, but it's the same process. We're going to take 2 times the x value of -3 plus 6 times the y value of -2 to determine does this equal -18. So I'm looking at a -6 plus a -12. Comparing still to the right side, -18. And when I combine, yes, -18 does equal -18 for that one. Now my second equation here with that -8x, same way, -8 times my x value of -3 minus my y value of -2, and I'm trying to compare to find out does this equal 22. So that's going to be a -24, no, excuse me, negative times negative there is positive. So this is positive 24, and subtracting that negative is going to be adding 2. Trying to find out if this does equal 22. So 24 plus 2 makes it a 26. 26 is not equal to 22, so this is not a solution for us. The ordered pair does not work in both equations. And then lastly, number 3, with a new system and a new ordered pair, we're going to plug those in again. So trying to compare if 12 is equal to the right side of my equation, 4 times y. Well, remember here, x comma y, so my y is 13 over 2 minus 8 times my x, where x is 7 over 4. So let's find out then. We're going to multiply 4 times that 13 over 2. So I'm thinking about 4 over 1 times the 13 over 2, right? It's always best to multiply fractions with fractions so you can keep those levels lined up. And so that's going to come out as a 26. And then 8 times the 7 over 4, again, use that as a fraction. So 8 over 1 times 7 over 4, that's going to put us at 14. So trying to find out here, does 12 equal this 26 minus 14? Well, 26 minus 14 does happen to be 12. So yes, that works. Now, got to check the second equation here with that 4y equals 12x plus 5. So 4 times my y value of 13 over 2. And I want to compare this with 12 times x, where it's 7 over 4, and then plus 5 for the end of my equation. So 4 times this 13 over 2, that's going to come out then as 26. Comparing with my other side, 12 times the 7 over 4, and that would be 21. Adding on 5, 21 plus 5 makes 26. So does 26 equal 26? Yes, it does. So we got both equations to check with our ordered pair. So indeed, yes, this is a solution to that system. In the next section, for number 4, we're looking for the solution determined from the graphs. So remember, the main goal for a solution to a system is looking for the intersection. I do have an intersection shown in that first graph. Your job is to identify the ordered pair where that intersection happens. This is at 3, 5. In the second image, you can see that I do have 2 lines there. It might be a little bit difficult to see though. The first line here, if I trace that in red, goes the whole way along, but that second line, look at those arrowheads in there. They're just at a different placement, but it's the same thing. It's overlapping. So this is what we call infinite solutions, or sometimes we call it infinitely many solutions. Both phrases are good. Both are acceptable. In that third graph, we can see that I have 2 lines shown and they are not intersecting. Please note that these are parallel lines. Those parallel lines have no intersection and therefore the system has no solution. So this number 5 here wants me to solve using the elimination method specifically. That means that when I add down the columns, I'm trying to cancel a variable. Unfortunately, I can see that that's not going to happen right here. Remember, for the elimination method, we need to focus on having the same coefficients in a column along with different signs. So one positive and one negative on the same value for those. And we don't have that, so we're going to have to do some multiplication here for this. Pick a variable that you want to get that cancel to happen on. I'm going to go ahead and focus on x right here. You could certainly use y just the same. Looking at the numbers only, just the numbers that we have on those x's, my coefficients, I'm going to have them do a crisscross. The coefficient x from the top is going to be my multiplier on the bottom. The coefficient on x from the bottom is now my multiplier on top. And now that's going to promise me that I have the same coefficient numbers that I want. Now I have to check out the signs. I already have a negative up top. I already have a positive on the bottom, so I don't need to do anything with my signs here. We are just ready to create this like a big distributive property. So we're doing 3 times negative 2x, that's negative 6x. We're doing 3 times positive 2y, that's positive 6y. And on the other side of the equals, we're doing 3 times the 6, that gets us to 18. Then for my second equation, again, distributing through across the whole thing. 2 times the 3x makes 6x. 2 times the negative 5y makes negative 10y. And 2 times the 5 makes 10. Now we're ready to add. Going to add down the columns. Negative 6x and plus 6x. Those are opposites. They're going to cancel out for us. Next column, we're doing 6y plus negative 10y. That's negative 4y. And on the other side here, we've got 18 plus 10. We get 28. We're left now with only one variable. Y is the only thing we have to worry about. This is a one-step equation to solve. I'm going to divide by my coefficient negative 4, divide the other side by coefficient negative 4 as well. So y is equal to negative 7. Remember now, you need to have 2 parts to that. You're looking for an ordered pair, so you need to have an x and a y. Pick one of your original equations and plug back into it. It doesn't matter which one you choose. I'm going to go ahead with the top equation. I think that 2, 2, and 6 might be smaller numbers than the 3, 5, and 5 that we have on the bottom, so maybe it'll make the top one a little bit easier to calculate with, but there's certainly nothing wrong with trying the bottom one if you would. So negative 2x and plus 2y equals 6. So which variable am I replacing? It's the y that we just solved for. Y is now being replaced with that negative 7. We're not doing anything with x. It's still here. We got to solve for it. So negative 2x plus this negative 14 equals 6. So remember, when I'm adding on a negative, I'm actually thinking about subtracting. So negative 2x minus 14, that says we got to add 14 to both sides to help cancel that out. Negative 2x then is equal to 20. Divide both sides by that negative 2 coefficient. So x is equal to a negative 10 for us. Now we know the value of both variables. Now you can give your solution as that ordered pair, x comma y, negative 10, negative 7. Don't forget, you can also type those equations into your Desmos graphing calculator when you want to check your answer. So moving over then to question number 6, we're going to solve this using the substitution method. So find one variable that is isolated all on its own, that's x equals. This variable that's isolated is my box, and I make the box in the other equation as well. Take everything that you know about x, everything that x is equal to, and that is what we are going to use to fill in the box. So we are keeping that bottom equation exactly like it is, except for this big empty box that we have. That box gets filled in with my x value. That means 2y minus 1. We're going to go ahead and distribute through. Okay, that was the substitution, took a variable out, put the expression in its place. So negative 3 times 2y makes negative 6y. Negative 3 times negative 1 makes positive 3. We're adding on y. This is equal to 23. After you distribute, combine some like terms. Negative 6y and positive y gives us negative 5y. Keep that plus 3, keep that equals 23. Two-step equation now, we're going to have to cancel the constant, subtract 3 from both sides. Negative 5y is now equal to 20. And when I divide both sides by my coefficient of negative 5, there we are, y is now equal to negative 4. So we're going to go on ahead, and we know one variable. Find the next variable. You need both the x and the y to be a part of this solution. Pick one of your original equations so that we can use it to help find x. I'm going to go ahead and use the top one since I want to find x, and the top one is already set up with x on its own. That should make it maybe a step or two faster for me. So with my top equation, we're going to go ahead and replace that y. What do I know about y? I just found that it's a negative 4. Plug that in. So 2 times negative 4 makes negative 8. And then we have to subtract that 1, so x is negative 9. You now know both of these values. Wrap them together in an ordered pair, x comma y, negative 9 comma negative 4. There we are. As I turn over and look at question number 7 here, we're going to solve these systems with any method that we choose. And so do recall that substitution and elimination are the most accurate versions. Graphing does risk that you are going to run into a fraction on your graph, or certainly there's the possibility that you might make an error in your counting for your intersection to be slightly off. So we do usually want to stick with substitution or elimination for that reason. When I look at question number 7 here, I'm going to try and determine whether that substitution or elimination is the better option for it. And when I look, substitution means that I want one variable isolated. And I do happen to have this letter y all alone. So for number 7, that tells me substitution's the better option. So that y that I know and everything about it is going to replace the y in my other equation. So I copy the top equation exactly like I see it, except for that letter y. It's now an empty box. Fill it up with everything you know about y, 1/2 x minus 2. And so we go ahead and distribute on over those parentheses. Keep my 2x exactly as it is. Take that negative 2 times 1/2, that's negative x. Negative 2 times negative 2 is positive 4. This equals 2. We're going to combine some like terms. 2x minus x makes 1x. You can write the 1 or leave it invisible. Keep the plus 4, bring down the equals 2. Subtract that 4 from both sides. So now we see that x is equal to a negative 2. We're going to go back to one of our original equations to find the other variable. I know x and I need y. I'm going to use the bottom equation since it's already got y alone. That might make it just a step easier to get to my answer. So 1/2 x minus 2. Take that x out, replace it with the negative 2 that we just solved. So what's y going to be? Do that arithmetic. 1/2 times negative 2 is negative 1. Subtract the 2. What's that leave us with? Y is equal to a negative 3. Put it all together now. My ordered pair is negative 2 comma negative 3. We go on over to number 8. And looking at that, again, trying to decide between substitution or elimination, I see one variable isolated all on its own, so that tells me that substitution is going to be a nice model to use here. So everything that I know about that y needs to replace the y in my other equation. Going to copy down that top equation exactly as I see it, 5x plus 2y, but y comes out, and we replace it with that whole expression to fill in the box, the negative 5 halves x plus 5. So now we distribute. We're going to bring down that 5x. It's this positive 2 that's going to get distributed. Positive 2 times the negative 5 halves x comes out then as negative 5x for us. Got to change my sign there. Okay, there we are, negative 5x. The positive 2 times the positive 5 makes positive 10. And bring down that equals 10. So combine like terms, 5x and negative 5x. Those are going to zero out for us. So we're looking at 10 equals 10. All my variables have canceled. This is a true statement. Anytime you have that true statement here, this is where we're getting those infinitely many solutions, or infinite solutions if you prefer that phrasing. But this would be on a graph. If you're picturing it, we're talking about overlapping lines, coinciding lines. So then we'll come to question number 9. So trying to decide if substitution or elimination is better for this. Well, substitution works if I have one variable completely isolated and on its own. I don't really seem to have that. Elimination is going to work best if I have one set of columns for my x's, my y's, my equals, and then my numbers. I don't really have that. So I need to try to rearrange and see if I can make this into a substitution or an elimination problem nicely. And I would say that it's probably either way. I could isolate the x in my top equation by just doing a subtraction on the 6y. That would make it nice for substitution. I could subtract the 1 from my bottom equation, have x isolated. That would make it nice for substitution. I'm going to actually go ahead and set this one up for elimination, purely just because we did the last two in substitution, so I want to make sure that you have a variety of them to study from. But if you're more comfortable with substitution, by all means, that would work. So to get that elimination set up, I want to have my x on the left side. For my bottom equation, I want to have my x and y both on the left. So I'm going to subtract x from the right and subtract the x again from the left for it. That is... And now I'm going to set this up intentionally. Since my top equation says x plus 6y equals 19, and it does the x first, then the y, in my bottom equation, I'm going to write it that way. I'm going to write the negative x first, and then I'll put that positive 2y. And it's now equal to 1. This is set up and ready. There you go. So now we can use the elimination. Now we've got the x column, y column, number column for it. We can go ahead and add. So x plus negative x cancels out. 6y plus 2y is going to give us 8y. And 19 plus 1 makes 20. We'll go ahead and divide both sides by 8. Simplify that fraction. I have a common factor of 4 between each of those, so y is 5 halves. Use that now to go back and find our x value. You always got to have the x and the y for it. Pick one of those equations that you want to plug into. I'm going to go with the bottom equation because I think that the 19 in that top might make my numbers a little bit too big to think about. So if my bottom equation then, oops, excuse me, I'm starting to write the wrong one. Okay, so bottom equation, 2y equals x plus 1. And we're going to replace y. Take y out, replace it with 5 halves. This is equal to x plus 1. So 2 times 5 halves makes 5, right? Thinking about it as a 2 over 1. 2 numerator, 2 denominator cancels. There's our 5 equals x plus 1. Subtract that 1 from both sides. So 4 is equal to x. There we've got two values, and that makes an ordered pair, 4, 5 halves. Now for that number 10, 7x minus 2y equals 8, and 14x minus 4y equals 10. This one, when I look at that, I am going to be choosing that elimination method because I see that I have an x column, a y column, and a number column. Now, am I ready to add them right now? No, I'm not. I don't have the same number, same coefficient with different signs on either of those. So I'm going to have to multiply. So I'm going to focus this time on y because I see that those are smaller numbers, so it might make it easier for me. So I focus on the coefficient for each of those. The coefficient from my top equation is 2. That's now my bottom multiplier. The coefficient is 4 from my bottom equation. That's now my top multiplier. And check out those signs. It's a negative on both of the y's that we are given. If I add a negative and a negative, that doesn't cancel. Those aren't inverses. So one of these items that I multiply needs to involve a negative. It doesn't matter which one you put it on, just use one of those values as a negative. Now we go ahead and multiply it through. So 4 times 7x makes 28x. 4 times negative 2y makes negative 8y. And across the equals, 4 times 8 makes 32. Second equation, negative 2 times 14x makes negative 28x. Negative 2 times the negative 4y is a positive 8y. And then across the equals, negative 2 times the 10 is going to give me negative 20. Now we are ready to add. So negative 28x and positive 28x there, we're going to add. That cancels out and gives us a 0. We've got negative 8y and positive 8y. Those are inverses. They cancel out. I have nothing left on the left side. Then we've got the 32 and the negative 20 to add together. That would come out as a 12. Does 0 equal 12? Absolutely not. This is a false statement that we get after all of the variables have canceled. This indicates to us that we have absolutely no solution. I'm trying to find an intersection for parallel lines. That's never going to happen. And then down below, the last two questions on that study guide, some applications. So at the amusement park, rides could be fast or slow. On a Tuesday, they sold 400 tickets and made $1,100. We know that fast ticket prices are $3 and slow ticket prices are $2. So how many of each were sold? Let's begin by setting up our variables. I'm going to choose to label F as a fast ticket, and I will use S to mean a slow ticket for us. So we have to write the two equations for this. So the number of tickets that we had is our fast plus our slow together, and that makes 400 tickets. The second equation needs to be based on the prices that we have. It costs $3 for every fast ticket, and it costs $2 for every slow ticket. So we have to multiply those values together to get our total sales. That's 1,100. Given this, when you look, is this going to be better for a substitution setup or an elimination setup? And I hope that you see those columns that we have going on. So that would tell me that elimination is going to be a little bit better here. We just have to multiply through this in order to make it happen. Pick the variable that you want to cancel out. It doesn't make any difference in this case which one you do. I'm going to say let's go ahead and focus on F. So my coefficient on F in the top equation is the invisible 1. That's now my multiplier on the bottom. Coefficient on F from the bottom is 3. That's now my multiplier on the top. This guarantees that I will have same coefficients. I'm going to check out the signs now. I have a positive F and a positive 3F. That won't work with inverses. So one of these multipliers now needs to be a negative. It doesn't matter which one you pick, just tack it on there. And big distributive. Negative 3 times 1f makes negative 3f. Then negative 3 times s makes negative 3s. And negative 3 times 400 on the other side of the equals gives us negative 1200. Across the bottom, multiplying by 1 makes that an easy choice. It stays the same. 3f plus 2s equals 1,100. Now we're ready to add. Negative 3f and positive 3f when we add cancels. Negative 3s and positive 2s makes a negative 1s, and negative 1200 plus the 1100 is going to be negative 100. Divide both sides by that negative 1 coefficient. I'm looking at s equals 100. Now we have to find the other variable for it. Go back to one of those original equations. I'm going to choose the top equation that we wrote because I think that those values are smaller and easier to work with. So if I know that fast plus slow is equal to 400, and I just found out that slow is 100, we're going to have to go ahead and subtract that 100 from each side to find out fast is 300. What does this mean now? We have to be able to explain our answer, right? So how many fast tickets did we sell, right? We have sold 300 fast tickets, and we sold 100 slow tickets. There we are. Now, example number 12 about Farmer John. He has 18 goats and chickens on his farm. Each goat has 4 legs, and all of the chickens have 2 legs. Now, his son Joseph went out and counted 56 legs on the farm. We just don't know whose legs they were. So, create a system of equations so that we can find the number of goats and the number of chickens on Farmer John's farm. So if we know that G is representing goats, and we know that C is representing chickens here. So what do we know? We've got 18 total animals. The goats plus the chickens gives us 18 animals. That's a good thing to know. And then we're also going to have to work with how many legs do we know? So for every goat that we see, it has 4 legs. And for every chicken that we see, it's got 2 legs. So we're going to have to multiply those amounts together to help find out their total legs and give us that 56. So in trying to decide how I want to solve this, again, I see that I've got columns of G's and columns of C's. That makes me think that elimination is a pretty good choice here. If I add right now, I'm not going to be able to cancel anything, so we will need to do some multiplying in order to make that happen. I'm going to choose to multiply with the C's here because I think that the 2 coefficient might make this a little bit easier for us. So my top equation coefficient on C is the invisible 1. I'll use that as my multiplier on the bottom. My bottom equation coefficient on C is a 2. That's now my multiplier up top. Check out those signs. They're both positive right now. And so I need to make sure that I get different signs. I need opposite signs. One of those values that we're multiplying with needs to have a negative. I'm going to put it with my 2 so that multiplying by the 1 on the bottom doesn't really require any work. It's just a rewrite. Multiply the whole way across now. Negative 2 times G makes negative 2G. Negative 2 times positive 1C makes negative 2C. And negative 2 all the way across times the 18 is going to be negative 36. Then on my bottom equation, multiplying by the 1 doesn't do anything, so it's going to keep it the same. 4G plus 2C equals 56. Now it's time to add. Negative 2G plus 4G gives us 2G. Negative 2C plus 2C is going to cancel out. And on the other side of the equals, negative 36 plus 56 gives us 20. We're ready to solve for G. Divide by that 2 coefficient on each one, so G must be equal to 10. Use one of our original equations now to help find the other variable. I'll go ahead back to my top one. Again, I'm picking it because it has the smaller numbers. 18 should probably be easier to work with than 56 for me. So G plus C equals 18 was what we had used, and I just found out about G. That is 10 plus C equals 18. To solve for C, I got to subtract that 10 from each side, so C must be equal to 8. Now, remember to explain your answer. What does this tell me? On the farm, there are 10 goats, because that's what G meant, and we have 8 chickens, because that was what C represented. I hope you're feeling a lot more confident with your systems of equations now. Have a great day.